Hello folks, this is Mr. Waters, and here is our last assignment before our spring break. And I know you guys are going to have a great spring break. We've been working pretty hard, and I think we've earned it. Okay, but anyway, so this assignment that you're about to see here, or the work that's going to go with this, is going to be due the Monday after we come back, which is the next blue day. So you'll have today and tomorrow officially to work on this and get it done before you go off on your break, okay? All right, so anyway, these are more related rates problems that have got some more complications and nuances to them. Now, not a lot, but just a little more work in the way of solving and writing the formulas is all. The procedure, the process, the logic is the same. Now, I didn't have a lot of questions on the last set of problems we've been working on. Okay, one question came to me by email, right? And I put that out, those notes out in on the last module as the notes about that answer to those questions. Okay, and so here again, if you've got more questions, send me an email, contact me, and we can either arrange a video conference, or I can just I can answer them by way of video like this. Okay, anyway, a hypothetical, and here's another situation. A hypothetical square grows at the length so that the length of its diagonals are increasing at a rate of 5 meters per minute. How fast is the area of the square increasing when the diagonals are 9 meters each? Now this is a lot like the circle problem, where the circle was increasing, right? Except that, well, it's a square. So the first step is we're going to draw a picture. So here's my square, okay, and we label it with the information, and this is step one, you understand. We label it with the information that we're given, and the information, and the quantities and the information that we're given, and the quantity, the thing that we're solving for, right? So it says here, there's the square, we're working with the area of the square, so yeah, the inside of this square is going to have some area, right? And then we're supposed to relate this area to the diagonal. So I'm going to put the diagonal right here. I'll use red for this. And I'll label that D. That's the diagonal. Well, we also know that the square also has sides to it. And we don't know a formula for the area of a square that relates to the diagonal, but we do know a formula that relates the area of a square to the length of the sides. Okay? Anyway. So let's see. So that's the first thing we're given here. Now, again, just like with the last problems, we're going to summarize. Step 2 is to summarize the information in terms of find, when, and given. Find, when, given. Find is the rate that we're supposed to be calculating. Okay, in this case, it says the area of the square. So remember, you want to think about the area of this square getting bigger and bigger and bigger, right? So this is going to be A primed, and that's going to be in terms of meters per, or actually square meters per minute, because it's area. Okay, well, when do we want to know it? Well, it says when the diagonals, that's this right here, this diagonal or that diagonal the other way, they're going to be equal, so we only need to draw one in. When the diagonal is equal to 9 meters. It says 9 meters each because the two diagonals are equal in length, but we only need to draw into one. Okay, so given, what are we given? It says that the diagonals, the length of this diagonal is increasing. That is, as the square gets bigger, the diagonal gets bigger, right? So the diagonal, that's the rate of change of the diagonal is 5 meters per minute. Okay? So this is not a static quantity, right? Because the square is getting bigger and bigger and bigger. We want to know what would the area be, or rather, what would be the rate of change of the area at the instant when the diagonal happens to be 9 meters. Okay? So this is what we're summarizing here. Now, step 3, we need to have a, well, I guess step 3, we need to have some formulas that relate these. Well, we need to have a formula that relates the diagonal and the area. That's going to give us our formula that we can then take the derivative of. Okay, but we only know this one here. We know that the area is equal to the side squared. I'm going to squeeze that over a little bit there. Okay, we know that the area is side times side. Well, we have to go a little bit further. That's what makes this problem a little bit harder, because we need a formula that directly relates diagonal and area. In other words, that'll give us the area as a function of knowing what the diagonal is. Okay, well, we don't have that yet, but we do notice over here, oh look, this is a right triangle, right? Side, side, diagonal. So I'm going to write it right here, because it's the Pythagorean theorem here. The diagonal is equal to the diagonal squared is equal to the side squared plus the side squared. So what we're doing here is we're seeking specifically a formula that relates diagonal and area directly. We don't have that, so we've got to solve for one over here. Okay, so the diagonal, because we can relate diagonal to sides. Well, okay, that's the diagonal squared is 2 times the side squared. And therefore, the side squared, if we divide both sides by 2, the side squared is equal to 1/2 the diagonal squared, right? Cool. Okay, so now we could square root both sides, but we don't need to, because over here we've got s squared. So we can substitute this 1/2 d squared for the s squared, and that's going to give us number 4, step 4, this formula that we need that relates area and diagonal directly. Okay, does that make sense? Scoot that over even a little bit more there. So now, so that's our formula, or actually, technically, we're still part of, oopsie, technically we're still part of step 3 where we achieve that formula. Now, again, this is the static relationship between area and diagonal. We need to know the rate of change of the area as it relates to the rate of change of the diagonal, because the thing is getting bigger, right? So now what we do, step 4 in fact, is going to be we take the derivative of that. Remember that as this thing gets bigger, area and diagonal are both functions of t directly. They're not they're functions of t. So when we take the derivative, we do a primed, right? And then over here, we take the derivative here using the power rule. 2 times 1/2 is 1. So that's going to be d. So that's the derivative of the outside, because we're using a chain rule here. The derivative of the outside is just going to be d times the derivative of the inside, which is d primed. Okay? So remember that we have to have an a primed and a d primed here. Okay, the derivative of d here is not 1, because it's not, it itself is a function that's changing. It's a function of time. So rather than 1 here, we put d prime. Okay? All right, so now that we've done that, we plunk the numbers in. That's step 5. Okay, a primed is what we want to know. So a primed is equal to d, which is 9, times d primed, which is 5. So a primed is equal to 45 meters squared per minute. And you see that comes out to be a positive because the circle is increasing. Okay? Now, so that's one. And in your work for today, you're going to have one or two of those to work on. Okay? So so number 2, I'm going to move this up a little bit here, here's another example. A perfect cube-shaped ice cube melts so that the length of its sides are decreasing at a rate of 2 millimeters per second. Assume that the block retains its cube shape as it melts. Okay? In other words, that the volume relationship would be the same. Okay, at what rate is the volume of the ice cube changing when the sides are 6 millimeters each? Well, you can see this is like the snowball problem, okay? So the rate of change of the volume is going to be negative because the thing's getting smaller. The volume is decreasing. Okay, so let's draw a picture. Okay, so I'm going to draw a picture of the cube here, just like this. Okay, and there it is. And then the volume over here, it's got, since it's a cube, oopsie, that's the volume, is the amount of ice inside the cube shape, right? And it's got, those aren't 5s, those are S's to relate the sides, right? So those are S's, right? Now number 2, so we've drawn the shape and we've drawn, what we know about the quantities that are involved in the problem, because they mentioned the side and they mentioned the volume. So now step 2, find when given. We're going to summarize what we're solving for and the information that we're given to solve it. It says we want to know at what rate is the volume changing. So that V primed is going to be what we're looking for. And that's going to be in cubic millimeters per second, right? Because cubic units are the volume units. And we're anticipating that that's going to work out to be negative. Okay, when do we want to know it? We want to know when the volume of the ice cube, we want to know at what rate is the volume of the ice cube changing when the sides are 6 millimeters each. So when when all the sides are exact, oopsie, not cubed, are 6 millimeters each. And then we're given here, the rate that we're given is 2. And it says the sides are decreasing. Since they're decreasing, we call that negative 2. Because remember, if the function is decreasing, its derivative, its rate of change is negative. Okay, so now number 3, we need a formula that relates these. Cool, well, that's pretty simple in this case. Volume is equal to side cubed, right? But remember, V is really V of t. And remember, S is really S of t. Those are functions. Now you can see it. Remember, those are functions of time, right? And so when we take the derivative, like we're about to do right now, step 4, I'll do it over here. Step 4, we're going to have derivative, that's V primed. Using the power rule here, that's 3s squared, right? And then that's the derivative of the outside. We're using the chain rule. The derivative of the inside is whatever s primed is, because remember, s itself is a function. That's why we're using what we called implicit differentiation here. Okay, so now there's our derivative formula. It's going to give us the v primed we want, right? And so we know v primed is what we want. Okay, s primed is -2. Oh, and s is 6. So we've got all the information we need here. So step 5 is we just plunk the numbers in. V primed is equal to 3 times 6 squared times -2, right? That's 36 times 3 times -2, right? That's exponent first. 36 times 3 times -2, that works out to be -216 cubic millimeters per second. And oh yes, it came out to be negative, because that's negative, and that shows us that the volume is decreasing. Okay, very good. So that's what we want for those two. Now we'll do one more on this video, right? And here is a ladder problem. This one is going to be a little more work, as you will see. Okay, let me focus this again here, make sure you make it as clear as possible. Okay, good. All right, so now these notes, of course, will be on Canvas along with this video. Okay, here's the situation. A 17-foot ladder is leaning against a wall and is sliding towards the floor. The foot of the ladder is, of course, sliding. As the top of the ladder slides towards the floor, the foot of the ladder will slide away from the base of the wall at a rate of 3 feet per second. How fast is the top of the ladder sliding down the wall when the top of the ladder is 8 feet from the ground? Now you're thinking, what? Well, all right, let's draw a picture. Here's the wall. Here's the floor. All right. Here's the ladder, which we're told is 17 feet long. Now, that's a static quantity. That's not going to change. The ladder's not going to get bigger. The ladder's not going to get smaller. So we can count on that value to be a constant. Now we're going to assume, by the way, that the wall is right angles to the floor, right? Typically they are. Now we're going to label this with our given information here. Well, we know the ladder, so let's give these other quantities here. They're talking about the height of the top of the ladder, the distance from the top of the ladder to the floor. So let's call that y because it's vertical. And they're also talking about the distance that the foot of the ladder is from the base of the wall. Let's call that x because it's horizontal, right? And you can see there, oh look, that looks like a right triangle, doesn't it? Which is going to give us a hint about the formula that we're going to need to relate the horizontal distance of the ladder and the vertical distance of the ladder that they mentioned up here. But first, find when given. What are we supposed to figure out? Well, in terms of the labels here, we want to, you can see that the ladder is sliding down like that, and correspondingly, simultaneously, the foot of the ladder is sliding away from the wall. So we want to know the rate in the few seconds that it takes for the top of the ladder to actually collapse to the floor. We want to know the speed at which that's flying towards the floor. So in other words, we want to know y primed, which, since this distance is getting smaller, is going to come out to be negative. Now, when do we want to know it? Well, it says we want to know it when the top of the ladder is 8 feet above the floor. That is, at the instant in time when this ladder happens to be 8 feet above the floor. Now, it says that the rate that we're given is x prime, the speed at which the ladder is flying away, right? At which the base of the ladder is flying this way. So x primed, this guy right here, the base of the ladder is moving away from the floor, away from the base of the wall at a speed of 3 feet per second. This distance is getting bigger, so that's got to be positive, right? Since this is an increasing distance. Now, step 3, I know what you're thinking. You're thinking, oh, well, all right, that's the Pythagorean theorem that relates x, y, and 17. So yeah, since the ladder is always 17 feet, we can actually put that right in the beginning because it's always 17 feet. It doesn't get bigger or smaller. So now, in one of our earlier problems, we knew what to do with this. To find this rate, to find the derivative here. Remember, x is a function of t and y is a function of t. So every time we see an x, it'll generate, we take the derivative of x here, it'll generate an x primed. And when we say y, when we take a derivative of y, it'll generate a y primed, right? So using the chain rule and the power rule, that's going to be 2 times x, 2 minus 1 is 1, but then times x primed, plus 2 times y times y primed. Always generate an x primed and a y primed because they're both functions of t. And that's a constant, so I didn't even bother squaring that because that's going to get to be 0 when we take the derivative. So we just did step 4. Now, if you remember doing this problem in one of our earlier homeworks, you remember that we don't have all the information we need here. As you see here, we've got, I forgot to label it up here. This is equal to y, right? That's the y value. So we know y. Y primed is what we're looking for. x prime we're given. The x we don't know. That is, we need to know at the instant in time when y is equal to 8, what would x be at that instant in time? Okay, well, so we're going to go back. This is where we have to seek some additional information, right? So we're going to say, oh, here, x squared plus y squared, that's equal to 17 squared. 17 squared is 289, I think, right? Right? So now the y is equal to 8, so we want x squared plus 8 squared is equal to 17 squared. That's 64. That's 289. 289 minus 64. That works. X squared works out to be 225 square root 15. So that means we've got additional when information that we didn't know in the beginning that we needed, but that x is at that point when we want to know y primed, we know that x has to be 15. So now we just plunk all that in. So this is step 5 here. 2, 15, x primed is equal to 3 plus 2, y is equal to 8, and then times y primed is equal to 0. So 2 times 15 is 30, times 3 is 90, plus 16, y primed, right? Subtracting, and then dividing by 16, y primed is equal to 90, negative 90, divided by 16, right? Because we had to, at first, forgot the 0, you had to subtract the 90 from both sides. So yeah, this is going to come out to be negative like we thought, and that's going to be 90 divided by 16 is, according to Mr. Calculator, about negative 5.6 feet per second. Right? So that says it's not going to take very long for the ladder to hit the floor, right? But that's the speed that it's traveling at. Okay? All right, very good. So that's enough for now on this video. We're going to have another one. I'm going to do another one in which we do a couple of other problems, and all of these problems like these will constitute your classwork and homework for these last 2 days before break. Okay? See you soon.